Hey, how's it going, everybody? So we're here to talk about section 4.4. Before that, there's like a couple things I should go back and talk about from 4.3. I started talking about these yesterday, but my internet crapped out. So I'm going to start from scratch here. Wait, hang on. I think I said all the wrong section numbers. I think this is 4.3 I'm lecturing about, but there's a 4.2 problem that I should do. So here's an example. Find a quadratic function with a leading coefficient of 1 so that 2, 3 is a critical point. Okay, I want a quadratic function. What's a quadratic function? I've taken an algebra class. I've taken an English class too. So I know a quadratic function is something like ax squared plus bx plus c. My answer is gonna be ax squared plus bx plus c if I can just figure out what are the right a, b, and c that'll make all this other junk true. This is my goal, is to find a, b, and c to make these things true. They said they want the leading coefficient to be 1. Well, that checks one of them off already. The leading coefficient is a is 1. So I know my function is now x squared plus bx plus c. So check, 1 out of 3 done immediately. What else do I need to know? They told me that 2, 3 needs to be a critical point. The key observation we need to make is that this isn't one fact, this is 2 facts. They stated it as 1 fact, but it's that 2, 3 is a point, and that it's critical. The fact that it's a point tells me that f of 2 better be 3. The fact that it's critical, what's a critical point? A critical point is a point where your derivative is 0, so f prime of 2 better be 0. How do I make sure these facts are true? Well, this is an equation I can solve, and this is an equation I can solve. I set up what are these 2 equations. F of 2, how do I figure out what f of 2 means? Well, here's a formula for my function. F of 2 is 2 squared plus b times 2 plus c better be 3. That says 4 plus 2b plus c better be 3. If I subtract 4 from both sides to clean it up a little, I get that 2b plus c equals negative 1. I could solve this for c, I could solve it for b, that's not really getting me anywhere. If I know what b or c is, I'll be able to come back to this equation and figure out what the other one is, but this equation by itself is not enough to tell me b or c. So let's set that one aside for now. What's the other thing going on? I know the derivative better be 0. What's the derivative? I know how to take derivatives. The derivative of this function is 2x plus b better be 0. I need hang on. The derivative for all x is 2x plus b. The derivative when I plug in 2 is the thing that better be 0. That says 4 plus b better be 0, so b has to be negative 4. Great, that's enough to figure out what c is. 2b plus c equals negative 1 says 2. Now I know what b is. Plus c equals negative 1, so negative 8 plus c better equal negative 1. Add 8 to both sides, c has to be 7. I have a, I have b, I have c. I have everything I need to write down my answer. The quadratic function they're looking for is f of x equals 1x squared minus 4x plus 7. Cool. There's a lot of these constraint type problems. What's this problem really asking? I think what it's really asking is for you to prove that you understand what a critical point is. That you need to know that the derivative equals 0 is a way to set up new and interesting, like you can ask that you understand that through different angles. And this is like another angle of saying I know what it means to be a critical point. Let's talk about 4.3. 4.3 is about global extrema. And it's mostly about how to do the work of 4.2 with doing less work. Like, a very common situation is someone hands a function, g of x is, I don't know what it is, and says find the maximum. The thing we learned in 4.2 is, well, we can find all the critical points, and we can draw a sign chart and figure out it increases, decreases, 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 increases, whatever. And we find, aha, this and this are the local maximum. When I've learned that it goes up, down, it might be like this or it might be like this. I don't know which of those two local maxima will turn out to be the high point. So what do? I take those points and plug them in, and that tells me what the global maximum is. And the idea is building the whole big sign chart feels like way more work when the actual solution came from just plugging in a couple points. What we'd like to know is there a way, when we don't care about all the increasing, decreasing, inflection point, when we don't need all that information, how quickly can we just find that something is the maximum without the whole sign chart rigmarole? This idea that the maximum is at one of those critical points gets us to one of these first big facts. Here's fact number one. There's two of them. Fact number one is the less useful one. But I'll say it first because it's the easier to understand one. If f of x is a continuous function on a closed interval, continuous is a technical term that basically means that you can draw the curve without picking up your pencil, is the idea. Is a continuous function defined on a closed interval If you haven't used the word before, a closed interval is one where it has the brackets, so it's from here to here, including the endpoints. If you have a continuous function defined on a closed interval, then f of x does have a maximum on that interval. And we already know it must happen at a critical point or at an endpoint of the domain. The reason this fact is useful is that once you know there is a maximum and it's at one of these points, I don't need to bother thinking about increasing, decreasing, whatever. I know one of these points is going to be the highest point of the curve. Plug them all into the function. The biggest number you get, that's the maximum. If I didn't know this fact, then I would still be thinking about increasing, decreasing. Is one of these points a maximum? Okay, if the maximum is here or maybe here, now I plug them in and figure it out. Once I know that there's a maximum, because it's a continuous function on a closed interval, I'm just plugging in the points. Let's talk about why this fact is true for a second. You can pretty much get there with a picture. When does a function not have a maximum? One of the ways it would not have a maximum is if it is in the place where the highest point would be, there's no point there. I can draw situations like this. That's why we need to have a closed interval, is so that that last point is actually defined. Whatever the end point of the domain is, there is a dot there, and if it would be the highest dot, you're allowed to use that and say that's the maximum. How could I get away from it? Say, well, I'm not going to use that dot, I'm going to put it down here. Well, now you broke the rule about it has to be continuous. Continuous means that wherever it looks like the highest point is going to be, there actually is a dot there. Closed interval says, and even if that's the end of the domain, you have to put an endpoint where the top is. Why else could you not have a maximum? Well, maybe you don't have a maximum because you go to infinity, like y equals x squared. That's an easy function. Doesn't have a maximum because it goes up forever on the right. We're not allowed to go up forever on the right because our domain is a closed interval. We're cutting it off at a point. When I cut it off, that becomes the maximum. Well, maybe I go to infinity somewhere in the middle. I can draw a function like this where it goes ooh, ooh. Well, now you're not defined on a closed interval because you're not defined at this point. Well, I'll just stick a dot here. Now we're defined. Well, now you've broken the rule about continuous. Like the idea is if you have a piece of string and you tie it down here and you tie it down here, no matter how long the string is, the fact that it has to come back down to where it's tied means it can only go so high, and that highest point is the maximum. That's the idea of this fact. The proof is technical, and it relies on knowing this technical definition of the word continuous, and we're not going to stress too much about that. Let's think about using this fact and when we can and can't use that for a couple of seconds. I'm going to write down a function. F of x is 3x cubed minus 8x squared minus 11. Find all global extrema. What's our domain? They didn't give us a domain, so we assume the domain is all real numbers, forever to the left, forever to the right. That's not a closed interval. It doesn't have a starting point and an ending point that are included. So we can't use that last fact. There's no guarantee that there is a maximum or a minimum. Before I think about taking derivatives and setting them equal to 0 and all that junk, just think real quick about what do I know about this function? This is a polynomial. It's cubic. It's got degree 3, which is odd. Remember all that stuff about end behavior you talked about in some algebra class? I have an odd degree polynomial. It has a leading coefficient as positive. That's enough to say that it goes up on the right and down on the left. Once I know it goes up on the right and down on the left, hey, we're done. You go up on the right, there's no maximum. You go down on the left, there's no minimum. There are no global extrema. A lot of understanding where the global extrema could be comes down to knowing what the function does at the ends. Does it go up on the right? Does it go down on the right? Does it have a horizontal asymptote? And these are things that you don't really use calculus for. These are things that you know from other classes. Or you can use calculus on them, but not the calculus we learn here. Okay. Let's try a different example. Or it's kind of the same function. Or it's the same example. It's the same function. 3x cubed minus 8x squared minus 11. Find all global extrema. On the interval from 0 to infinity. Aha! So now, it's still odd function leading coefficient. I know it goes down on the right and up on the left, but we've taken some scissors and cut this part of the function off. That got thrown away. Whatever it's doing at 0, it stops there. Maybe it goes up and down a million times, but in the end it's going to go up forever on the right. Going up forever on the right tells us there's no maximum. But it doesn't go down forever anywhere. I know it only goes up on the right. There's no room for it to go down to infinity in between because I got a closed interval on the left end. So there is a minimum. Where is it? It's at a critical point or an endpoint. Our endpoint is 0. What are our critical points? Let's take the derivative. F prime of x is 9x squared minus 16x. When do you equal 0? X 9x minus 16. When do you equal 0? I got it factored. That's at x equals 0. Or 9x minus 16 equals 0. That's 9x equals 16. That's x equals 16 over 9. The only possible locations of the min are x equals 0 or x equals 16 over 9. These are the critical points. Or x equals 0, the endpoint. X equals 0 is listed twice. I don't have to include it twice. There's two reasons. It might be the critical, it might be the minimum. How do I know which one's the minimum? I could do a little sign chart, increasing, decreasing, whatever, but that's overkill. Let's just plug in these numbers. What's f of 0? What's f of 16 over 9? f of 0 is 0 minus 0 minus 11 is negative 11. F of 16 over 9 is, this one's harder, 3 times 16 over 9 cubed minus 8 times 16 over 9 squared minus 11 gives me negative 19.42. Which of these is the minimum? That one's lower, that one's the minimum. I know one of these points is the minimum, and whichever one's the lowest must have been the minimum. So that's it. The minimum is this point, 16/9, comma, negative 19.42 dot dot dot. Maybe I would convert that to a fraction if I wanted to be fancy. The way you phrase this is actually super obnoxious. You're going to be tempted to say the minimum is 16/9. That's not the right thing to say. That's definitely wrong. You can say the minimum, that 16/9 isn't, when I talk about the minimum means what is the lowest y value that goes on. If I'm talking about what is the minimum, it is that y value is the thing that is the lowest, right? The x value isn't what the minimum is. The x value is where the minimum happens, which is relevant. If my boss says maximize profit, and I come back and say the maximum profit is $8,300,000, whatever, and I say, well, okay, what do we do to make that happen? That's the useful piece of information. That's the immediate second question. It's not just what is the lowest that it can be, or the highest. It is what do we do to make that, or what do we do to avoid that. The minimum is at x equals 16/9 is a true statement, but it feels like you're avoiding the question of what is the minimum. If someone's asking what is the minimum, I would say the minimum is negative 19.42 occurring at x equals 16 over 9 is the most precise way of saying what is the minimum. You can get all that information just with an x coordinate and a y coordinate and not stress so much over the words, though. Is this okay? That's I don't know why I'm saying is this okay. I'm all alone in this closet. Here's an example. Let's try one with a different interval. Let's go with the same function. Let me grab this and copy it. I got most of it. Here's a function, find all global extrema on, let's try the interval negative 2 to 1. Aha, this time it is an actual closed interval. I can use that fact that we said at the start in its full force. No worried about there is a max, there is a min. Where do they happen? They must happen at a critical point or an endpoint. So, what's going on? This is a situation where, like, I'm worried about, does the function go to infinity somewhere, or does it not exist at the place where the minimum would be? When it's a closed interval, that stuff can't happen. There is a minimum. Where could it be? It could be at the endpoints. It could be at a critical point. It's at one of those. I just need to find those critical points and endpoints. The endpoints are negative 2 and 1. The critical points are, what are the critical points? I found them a second ago. It's the same function, so they're not changing. They are 0 and 16/9. What's 16/9? That's 1 and 7/9. 1 and 7/9 is outside of our interval. We don't care about 16/9. It would be a critical point, but it's not in the region we're talking about. So the maximum and minimum exist, and they happen at some of these points. Let's plug in these numbers. What's f of negative 2? What's f of positive 1? What's f of 0? F of negative 2 is 3 times negative 2 cubed, minus 8 times negative 2 squared, minus 11. 3 times negative 8 is negative 24. 8 times 4 is 32, so this is a minus 32, minus 11. These are all negative. I'm getting negative 57, 58. Negative 68 is what I got. Don't circle it until you know it's an answer. What's f of 1? F of 1 is 3 times 1 cubed, minus 8 times 1 squared, minus 11. That's 3 minus 8 minus 11. Negative 5 minus 11 is negative 16. What's f of 0? That's 0 minus 11 is negative 11. I look at these numbers. One of them's the max, one of them's the min. You're the highest. The max is 0, negative 11. You're the lowest. The min is negative 2, negative 68. Cool. No, don't do that. I don't want that. Cool. That's the max, that's the min. Once I knew they existed, it just came down to checking all the possibilities and not worrying about increasing, decreasing, whatever. I can, now that I've plugged in these numbers, I can tell you some stuff about the increase, decrease, whatever. At negative 2, I had negative 68. At 0, I had negative 11. And then at 1, I had negative 16. So I can tell you it was increasing here and decreasing here. If I had done that before plugging in these points, I would have worked out it's increasing and then decreasing, but I wouldn't have known which one of these points was lowest. Just knowing that you increase, decrease is enough to know the middle one's the maximum, but I'm going to have to plug it in anyway to see what the maximum is. One of these two endpoints will be the minimum, but I have to plug them both in to see which one's the lowest. I wouldn't have skipped any steps. I'm going to end up plugging in all three numbers anyway. The point of this section is kind of, when you just need the max min, just skip to plugging in the numbers, if you have some reason. On the test, I make kind of a big deal about making a sentence about why do you know this number is the maximum or the minimum. So in this example, I need to write down, this is a closed interval, there is a maximum or minimum. This is my fact one that I'm using. There's going to be a couple points on the test about, did you say, I know there is a max because it is a closed interval? Or I know there is a max because it's a closed interval, and then I checked all the possibilities, and it turned out this one is the maximum. So that's fact one. Let's talk about fact two, which is the better one. Fact two is about concavity. When looking for global extrema on an interval. If the second derivative of your function, so of a function f of x, if the second derivative of that function is always positive, or if it's always negative on that interval, which is kind of a big ask. First of all, I don't really like taking the second derivative unless it's easy, so if my function has a really easy second derivative to take, I'll go ahead and try this fact out. But I need to be able to look at that second derivative and just glance at the formula and say, hey, I know that this function is always positive. Just sometimes you can look at something and, hey, you're squared, that means you're positive. You're squared and then you added a positive number to it. That means you're still positive. You're hoping that you get something where it's automatically always positive. If I write down x cubed minus 9x squared, well, a positive minus a positive is not guaranteed to be positive. A lot of functions you can't look at and know whether the answer you get back will be positive or negative. Sometimes you can. We're hoping that it's easy to take that second derivative and that it's easy to look at that second derivative and check that the formula only spits out positive or negative numbers. And I really only care about what's happening on the interval we're trying to maximize it on. So suppose something is always positive on that interval, or always negative, then there's at most one critical point in that interval. And if it does exist, it is the global minimum. On that interval. Or maximum. If the second derivative was negative. What's going on here? If your second derivative is always positive, then you're concave up. There's three ways you can be concave up. You can be concave up with the full smile, where you have a minimum, and there's only one critical point, and that critical point is the minimum. You can't possibly turn around and have another critical point without switching concavity, is the point. Or maybe you're like this, and you don't have a critical point. Or maybe you're like this, and you don't have a critical point. There's these possibilities where you don't have a critical point, and in that case you don't have a minimum, because either it's at the end point, or it doesn't exist, or whatever. But if you are always concave up, if there's a critical point, you get to automatically know that that critical point is the minimum. If you are concave up, it's the maximum if you are concave down. All the same things apply for the Frowny. These things don't have a critical point and don't have a global max, or they might if there's an endpoint here to label as the global max. This one, where it does have a critical point, that critical point is automatically the global max. This is most of the time, what you want to be doing in these problems is take the derivative, set it equal to 0, there's the answer. But there's a big gap of knowledge between here's the critical point, how do you know the critical point is the answer, that I make a big deal about, and it's going to be emphasized on the test, is how do you actually know. The practice exam is posted, by the way. You can see the problems where I say why you know this critical point is actually the max or min or whatever. When this works, this is the nicest thing in the world. It sort of depends on, you need to be able to use the second derivative. But, yeah. Let's try this example out, and let's try a word problem that uses this example. I want to plant a garden. To protect it from deer, I'm going to build a fence. I'll use the north side of my house. So one side of the fence, one side of the garden will be my house. I don't need to fence that part. I don't need fencing on that side. I have 68 feet of leftover fencing. What's the biggest rectangular garden I can make with it? So, there's a lot of these word problem type problems, and they all boil down to maximizing or minimizing something. Here I can see the question we're being asked is what's the biggest? We want to maximize. What do we want to maximize? They didn't hand us the function. The hard part for us is going to be building the function. Once we have the function built, we're basically using the techniques we just learned to find the maximum of that function. What do I need to maximize? How do I measure the size of a garden? I guess I would measure area, is how you measure a region. So we want to maximize area of the rectangular garden. They told us it's a rectangle. It's pretty traditional to draw a picture for these problems. Here's my house. Here's me. How's it going? I'm staying inside. My garden needs to be a rectangle with beautiful flowers. With a leaf, 2 leaves, with a sad deer because there's a fence around my garden. I want to maximize the area of a garden. How do you find an area? It's a rectangle. Area is length times width. A very common thing that happens is when you make your first attempt at writing down what is the thing you want to maximize, what is my function? The area of a rectangle is the length of the rectangle times the width of the rectangle. So my area is length times width. I can't do calculus on this function. Why not? A, it's got 2 variables, and B, I don't have a domain. Like, just make the length and the width both really big. The common setup is your first attempt at writing down your function to maximize has too many variables. We're only in Business Cal. We're not ever going to talk about derivatives of functions that have lots of variables in them. We only deal with one variable at a time. We got too many variables. The way we fix that is we need to identify a constraint in the problem. They gave us some extra piece of information that lets us cut down the number of variables. What is going on here? They told us we only have 68 feet of fencing. So that tells us a fact about these length and width that let us get rid of one of the variables. I should label which one's the length. Let's call that length. Let's call that width. This other side is going to be the length again. This side is also the width, but I don't care about this one because I don't need fencing on that side. So the fact that we need 68 feet of fencing, or we need to use at most 68 feet of fencing, tells us something about length and width. This needs to be fenced, and this needs to be fenced, and this needs to be fenced. So the length plus the width plus the length again needs to be at most 68. First thing I want to do is I don't want to deal with this less than or equal to. If I want to make the biggest garden possible, I'm going to use all the fencing, right? If you handed me a solution that didn't use all the fencing, I'm just going to say, well, make it a little bigger, use the extra fencing. That wasn't the maximum, right? The biggest possible will use all they give us. I got 2 length plus width equals 68. Pro tip, if you make an L in math, make it like a cursive L so it doesn't look like a... I guess capital L would have worked too. Yeah. Oh god, that reminds me of my favorite... I love this joke. This is a Mitch Hedberg joke. I have a couch that is shaped like an L, lowercase. Why? It's the most unsatisfying thing in the world to tell a joke by yourself in your closet. I have a constraint, 2L plus W equals 68. I can take that and solve it for either variable. It's easier to solve for W, so let's do that. W equals 68 minus 2L. And now if I plug that into my area function, length times width becomes length times 68 minus 2L. Now I have a real function of one variable. If I distribute that in, 68L minus 2L squared. I should, when I do this, I should think about a domain. When you build your own function, part of building it is figuring out what numbers actually make sense in that function. And the domain makes a big deal on how you solve the problem. If my domain turns out to be a closed interval, that's great. If my domain is not, then, it makes a difference. I gotta think about these things kind of carefully. How big and how small could the length and width be? What's the smallest my length could be? Well, it's definitely got to be non-negative. Could L equal 0? Should I cut out 0 also? Which of these should it be? Well, what happens if length is 0? That means I'm just building a fence right next to the wall. I have 0 length. My garden is just a fence that I built right up against the wall, which was a dumb thing to do. It's reasonable to say that's not a garden. The problem was about building a garden, and you just built a fence next to a wall that has no area at all. And that's a reasonable thing to say. But from having looked at these facts, I know that if 0 is included as an endpoint, like when you allow the endpoints to count, life is better. Calculus is nicer if I have a closed interval. Am I going to accidentally get the wrong answer? Well, there's no way the biggest garden, like if I did the problem and it said the answer is build no garden at all, just build the fence next to the wall, that's definitely not going to be the maximum. I can make up any number and get my garden to have some area. Building the fence next to a wall will give an area of 0. So, it's not going to accidentally give me the wrong answer if I let 0 count. The only thing that's going to get mad is people who say that doesn't count as a garden. So go ahead and let it count. Let's let L equal 0 if we can. The other reason we might want to say don't let L equal 0 is if you can't plug 0 into the formula. We can plug in L equals 0. It's fine. You get 0. Yeah, not a big deal. What's the biggest the length could be? Well, if I think about just making it as long as possible, and that's going to mean having as little width as possible. Again, it's going to mean build a fence, and then build another fence right on the other side of it, with no width in between them. That maximum, if you use no width, then your length will be half of 68 is 34. The biggest the length can be is 34. Can we actually let it equal 34? Same deal. It doesn't make sense to call that a garden, but it doesn't break the calculus and it might make the thing easier. If we get to let it be a closed interval, like I can plug 34 into this function, presumably I'll get 0 because the area should be 0 there. So yeah, go ahead and let it equal the endpoints. Now I have a closed interval. I can do the snazzy thing where I know there is a minimum. Let's try and do our fact 2 instead of fact 1 though, because we used fact 1 before. What's the derivative of this function? Derivative of that is 68 minus 4L. It's not hard to take the second derivative. Let's take the second derivative. Second derivative is just the number negative 4. Hey, the number negative 4 is always negative. If we find a critical point, we automatically know it's the maximum. Do we find a critical point? Critical points come from where does the derivative equal 0? Does the derivative ever equal 0? Does 68 minus 4L ever equal 0? Does 68 ever equal 4L divided by 4? You get 17. L equals 17 is a critical point. It is in the range between 0 and 34. It's right in the middle. So yes. So L equals 17 is, I'm tempted to say it's the max. It's where the max happens. At this point, we usually have to go back and say, what is it they're actually asking for? Did they say, what are the dimensions of the garden? What is the area garden? They said, what is the biggest garden? That's sort of a vague version of the question. I should probably give all the information because I'm not sure what they mean. We found the length of the garden has to be 17. What's the width? The width is 68. I have a formula. 68 minus 2L gives us the width. I know that's 68 minus 2 times 17. I would care about the garden where we use length of 17. That's 68 minus 34 is 34. So we can say the biggest area, the biggest garden possible is 17 feet by 34 feet for an area of, I can multiply those and find the area is, do a calculator. What is 17 times 34? It is 578 square feet. That's the biggest we can get this garden to be. That's maximizing. That's when you can use the second derivative. And that's it for 4.3. Videos are already posted for 4.4 for the rest of Chapter 4 and all of Chapter 5. I'm going to tune in tomorrow to go through the practice exam. And, see you around.